Okay, this part is not in your book, but it is the application of the scientific method that I'd like to look at. Ptolemy was the early Greek philosopher who believed in laws of nature that just made sense but need not be tested, and Copernicus came later and used careful measurements to verify his model. Let's start with the movement of stars, sun, moon, and something that you and I and Ptolemy can all see. So, if we were to look up at the sky at night, what would we see? If we look at all night, we would see the stars move like this. In the course of the entire night, and in fact day and night together it would happen, they would make one big circle. Not only that, no circles would cross each other's path, and they all have the same center. It is an interesting observation that there is one star right in the center. So it is the only star in the sky that doesn't move all night long. The direction of this star is always straight north from where you are standing, and I would like you to remember its name, Polaris, or the North Star. It's also interesting that all the stars keep the same distance from each other. That means they always stay in the same groups, which we call constellations. I would like you to remember the most easily identified group in the sky. It looks like a spoon, so it is called the Big Dipper. Whenever we see the Big Dipper, we always follow the last two stars in the scoop to find Polaris and know which way is north. So how do you explain what we all see in the sky? It's easy. The Earth has, but to Ptolemy, the Earth has a glass sphere surrounding it with the stars pasted into the glass. It spins around the Earth once each day. Since it's clear, we can't see the sphere, but we can see the stars spin through the sky. Whenever we look straight north, we see a point that never moves, so that is where Polaris is. This, of course, explains our observations, but it also requires everything in the universe except the Earth to coordinate a lot of the movement. Then we have the problem of the planets, Mercury, Venus, Mars, Jupiter, and Saturn. They look like stars, nice and bright, but they don't behave like stars. They never stay in the same spot compared to the stars. They will be in one spot on Monday and a different spot on Friday, and they always keep changing. Even weirder, if you watch their position change over many nights, they will actually do loop-de-loop. They'll actually do loops in the sky. Here's a picture of what a planet looks like going from one day to the next over several days. It's no wonder they were called planets, which is the Greek word for wanderer. So the straightforward explanation is that planets are not in the crystal sphere but are in their own spheres and somehow go in a loop-de-loop path around the Earth. The ones that appear to move faster from night to night are in closer spheres, and the slower planets are farther away. It is also possible to see the sun and the moon shift their positions in the sky from day to day, so they were given spheres also. Only their positions make smooth paths. So putting it all together, Ptolemy had one crystal sphere with stars, 5 crystal spheres with planets in them, and 2 more crystal spheres, one each for the sun and the moon. They all rotated around the Earth once every 24 hours. but they slightly shifted their positions from week to week so that the positions of the sun, moon, and planets gradually drifted away from the positions of the stars. To Copernicus and practitioners of modern science, this model could work, but it seemed too complicated, too hard to control all the moving parts. History has shown since then that the simplest model that explains all the observations is usually the best model. Even worse, however, is a model that gives false predictions. In this case, Ptolemy had made tables used to calculate the locations of many planets and stars, and by the 1500s, in the time of Copernicus, they were all off. Copernicus needed a model that was more simple and that truly predicted the locations of the stars and the planets. One thing that had been proposed earlier to simplify the model was to keep the daily motion of the sun, moon, and planets still and just have the Earth turn once every 24 hours. That way, if the Earth turned once every 24 hours, it would be a much simpler way to view all the other things going around the Earth. The second big change in the model was to make the universe heliocentric. I should say the solar system heliocentric, or sun-centered. In this case, the sun is in the center of everything, and all the planets go around the sun. This nicely explains the loop-de-loop paths of the planets, because they travel different speeds. So when the Earth is catching up to the orbit of another planet, it looks like it's going one direction, but then when the Earth passes a planet, it looks like it's going the other direction. Now came the hard part. Copernicus's heliocentric model was simpler, predicted the behavior of planets better than the Ptolemy Earth-centered model. By modern scientific standards, it wins, and in modern times, nobody believes Ptolemy's model. We believe Copernicus's model. In his day, Copernicus didn't even want to publish the results because leaders in society, based on religious arguments, needed the Earth to be at the center of the universe. Also, there was also the strong belief in the Greek models of the world, especially the models of Aristotle. There were also some practical problems. If the Earth spun once every 24 hours, we should be traveling about 1,000 miles per hour along through space compared to the space around us. Why don't we feel a 1,000 mile per hour wind or see a falling leaf whip past us at 1,000 miles per hour? The answer is the air is actually dragged along the Earth's surface, so it's going just as fast as us until you get some ways off from the surface. You also might ask why we don't feel a force prying us off the Earth's surface. Just like we feel a force pulling us off a merry-go-round when it's spinning, we actually do feel this force. In fact, it is greatest at the equator and almost nothing at the poles. It's for that reason you weigh about a small fraction of a pound less when you are at the equator.